Hello, my name is Kara Conway, and my research project is on the use of fuzzy logic in decision-making processes. This presentation explores what fuzzy logic is, how it works, its real-world applications, and situations where its use in decision-making is more effective than other popular methods, such as probabilistic methods. I explore fuzzy system by implementing an employee evaluation system that uses fuzzy logic. So what is fuzzy logic? It's an approach to decision-making that diverges from the use of conventional binary logic. While traditional computer systems rely on binary values that are either true or false, or 0 or 1, fuzzy logic allows for a much more nuanced approach where degrees of truth are possible. It dates back to 1965 when Lotfi Zadeh was working on how to have computers understand natural language, which is not easily converted into binary values. He wrote the paper titled Fuzzy Sets, which outlines the need to formalize decision-making in situations where traditional binary logic falls short. In natural language, we allow statements that encompass relative truth. This is something that we see every day in our conversations. An example of this is answering the question, how cold is it outside today? The answer to this question isn't simply yes or no. It can be answered by a variety of statements, such as not cold at all, a little bit cold, or freezing. Since it's not possible to label any one of these statements as absolutely true or absolutely false, this is where fuzzy logic comes in. There are three basic elements of a fuzzy logic system. The first element is a fuzzy set, which are groups of input and output variables that represent a fuzzy system. Next, we have membership functions, which describe the degree to which an element belongs in a set, with 0 being completely not a member, 1 being completely a member, and anything between 0 and 1 being partially a member. Fuzzy sets transform crisp inputs into variables through membership functions. Membership functions are characterized by triangular or trapezoidal functions that are defined by the length of their bases and the slope of their sides. The third element of a fuzzy system is production rules, which are the blueprint of the fuzzy decision process. They represent human knowledge and follow the if-then format. Some other important elements of a fuzzy logic system are the processes fuzzification and defuzzification. Fuzzification is the process of assigning an input of a system to a fuzzy set with some degree of membership. Defuzzification is the process of converting the fuzzy output into a crisp value that can then be used for decision making. This example shows the difference between conventional and fuzzy sets. We use the example of defining an individual's height as tall. This is subjective. For example, one person may say that 6 feet and above is tall, while another person's idea of tall might be 5 feet 10 inches and above. As we can see from the figure on the right, conventional sets have well-defined bounds. So 5 feet 10 inches or 177.8 centimeters always falls in the tall set no matter what. But it belongs to both the average and tall fuzzy sets, depending on the degree of membership that it has. This is because fuzzy sets overlap, typically by around 25%, to represent the vagueness that occurs in the real world. So the fuzzy sets allow us to have vagueness that occurs when certain people say 5 feet 10 inches is tall or it's average. So there are definitely both pros and cons of fuzzy logic. The pros are that it does a good job of reflecting real-world problems, it works well with imprecise data, and it has lower hardware requirements than traditional Boolean logic does. The cons are that it depends on human expertise for the definition of production rules. as we saw in the previous example, language is subjective. So it does rely on humans to tell it what is what. It also has a limited range of scalability and a lack of standardization, unlike traditional probability or probabilistic models are very standardized. So comparing fuzzy logic to probabilistic models. Probabilistic models provide a much higher level of precision by assigning a quantitative measure of certainty through the assignment of probabilities to events. So they are better suited for when probabilistic information is available and uncertainty can be quantified. They also have a much more formalized framework, and they are better for situations where a well-defined structured approach to uncertainty is necessary. On the contrary, fuzzy logic is better in situations where uncertainty cannot be quantified, or we want to represent human logic or human thought processes, or the nuances of human language, as we've covered. So fuzzy logic does have many applications in the real world. Some of these are automated vehicle control, altitude regulation for aircrafts and satellites, natural language processing, artificial intelligence, facial recognition, and automotive systems controlling traffic and speed. Natural language processing is an application that really goes back to what we've talked about on previous slides, where we know that the human language is very nuanced, it can be very subjective, and certain words can have multiple meanings, which can be hard for a computer to understand. So the good thing about fuzzy logic is it is able to account for some of that vagueness or uncertainty or nuances that traditional applications using probabilistic models would not be able to do. An example of a fuzzy system that I implemented is an employee evaluation system. The goal of this system is to assign scores for an employee based on 3 professional areas: leadership, performance, and punctuality. The system uses the skfuzzy Python package to create a fuzzy control system based on given inputs and outputs and links them to production rules that I wrote. First, a user inputs a score for each category from 0 to 100 based on a general rating that they give for an employee performance. These 3 parameters are outputted into an auto membership function and then mapped to values low, medium, and high, which are in the fuzzy set. Next, crisp scores are defined for each output score, which are poor, below average, average, above average, and outstanding. And for instance, outstanding would map to high values and poor would map to the lowest values. So here are the production rules that I wrote for the system that follow human reasoning and instruct the system about which combination of categories map to which score. So one example of a production rule in the system is if degree performance is high and leadership is high and degree punctuality is high, then evaluation score is outstanding. The fuzzy control system simulation encapsulates these 9 production rules. And the Fuzzify evaluation function uses this control system simulation to compute a crisp score that's outputted from 0 to 25, and then a corresponding performance category for each employee. So here are the results. The demonstrated fuzzy logic algorithm exhibits efficiency in evaluating employee performance based on numeric user input. For example, inputting scores of 75 for leadership, 82 for performance, and 80 for punctuality yields an evaluation score of 18.229, and the membership function categorizes the employee's performance as above average, which aligns with the expected outcome based on the provided scores. We can visually see this in the illustration, which shows that the membership value is 0.7 for our score, which causes the score to fall in the above average category rather than the average category because they do overlap. This tells us that the elements have relatively strong associations with the set because the membership value is 0.7, which is pretty close to 1. In conclusion, the use of fuzzy logic over probabilistic models is rooted in its ability to represent imprecise data, a challenge that is present in other approaches such as probabilistic models. Fuzzy logic's proficiency in handling partial information, coupled with lower hardware requirements, make it an ideal choice in scenarios where uncertainty and imprecision are prevalent. However, it is important to consider the specific problem context and choose a model that aligns best given the nuances of a specific scenario. Thank you.